Alright, so let's continue where we left off last time. Just a quick recap. So we're looking at the problem of source compression, where we're assuming that the source sequence is a random sequence of length n, and it is distributed according to some distribution pxn. Right? Symbols are drawn from some finite alphabet, and for now we're assuming that this source distribution is known to us. All right. The goal is to compress this n-length source sequence into a k-length code word, but this k can depend on the source sequence. So it's a variable length compression scheme that we're looking for. And the goal is to come up with this encoder and decoder, or compressor and decompressor, that minimizes the expected length of the compressed sequence. Right? Or in other words, which minimizes the rate, which is the normalized expected length. And we're looking for variable length compression schemes with zero error. So in other words, when you decompress the compressed sequence, you should recover the original sequence, the source sequence, with probability 1. Right? And for this, we already saw what the optimal compression scheme is, assuming you don't have any computational complexity constraints. The optimal scheme is you just take all of the sequences, all of the source sequences in decreasing order of probability, and you assign compressed strings of increasing length, one after the other. This particular scheme is of course optimal, and we also derived an upper bound on the rate of this particular compression scheme. So the expected length happened to be the entropy of the source. So the rate is 1 over n times the entropy of the source. Right? So what we will be interested in most of this course is what happens when n is very large. So you have a source sequence of sufficiently long length, or in other words, you're trying to compress files that are suitably large. All right. So in that case, what happens to the rate? The rate is h of xn divided by n, and we'll be interested in limit as n tending to infinity h of xn by n. All right. So this is the asymptotic rate for a particular source, and we'll be interested in what is the achievable rate. We know that it is equal to h of xn by n, but the question is, for what sources does this converge to a well-defined limit? For example, what happens when xn is an IID source? What happens when xn is a Markov source? And so on. All right. In general, this quantity, limit as n tends to infinity h of xn by n, this is called the entropy rate. And we'll be interested in what is the entropy rate for specific classes of sources. Towards the last part of the previous lecture, we looked at various properties of the entropy, and today we'll look at some more properties of the entropy. So the entropy is, by definition, h of x equal to summation over all possible x in the source alphabet, p of x log 1 over p of x. And again, there was a few points that I made, that h of x, although we're using the notation h of x, it's not really a function of the random variable, but rather it's a function of the distribution. And you have to be careful about what happens when the sum of the probabilities are equal to 0. That needs to be handled a little bit delicately, which is not so much of a problem when it comes to discrete sources, but when we eventually go to continuous sources, that point will become important. All right. And the entropy was interpreted as the amount of randomness that is present in the source. All right. The more random the source is, the larger the entropy is going to be. And if you get to know the realization of the source, then it means that you've got more information. So the interpretation is that more random the source, more info you get by observing the source. All right. And clearly the amount of information that you need to convey is the minimum number of bits you need to represent the source, or on average what is the minimum number of bits that you need to represent the source, which is equivalently the minimum expected length of the best compression scheme. Right? Okay. So some basic properties of the entropy that we saw was that the entropy of any random variable, any discrete random variable, is always non-negative. When is the entropy equal to 0? Correct. Effectively, if x is deterministic. So the entropy can be 0 only if there is one symbol which occurs with probability 1 and all of the other symbols occur with probability 0. All right. So that's an important point. We'll also see that the entropy is maximum when the distribution is uniform over a particular alphabet. All right. But we also defined this notion of joint entropy of a pair of random variables. So h of x comma y is defined exactly as we did for the standard entropy, but by taking x comma y, the pair x comma y as a single big random variable. Right? And the conditional entropy was defined in this particular fashion. And we saw that using these definitions of joint and conditional entropy, we have the following chain rule, which says that h of x comma y is h of x plus h of y given x, or it's also equal to h of y plus h of x given y. Right? We'll be reusing many of these concepts over and over again, so it's good to be fully familiar and comfortable with these ideas. Okay. Any questions so far? Yeah. All right, just using the properties that we've seen previously, suppose that x1, x2 up to xn are independent random variables, then what is h of xn equal to? Correct. It's going to be equal to, well, if you just apply the chain rule, then you would get that this is equal to summation I equal to 1 to n h of xi given x1 up to xi minus 1. But if the random variables are independent, then pxi given x1 through xi minus 1 is equal to pxi. The conditional distribution is equal to just the marginal itself. So this is nothing but summation I equal to 1 to n h of xi. Okay, hopefully that's fine. Okay, so suppose I have two random variables x and y, which are potentially jointly distributed. Some they may be correlated with each other. What can we say about h of x given y versus h of x? Can we say that one is less than or equal to the other? Okay, the claim is that h of x given y is less than or equal to h of x and y.
Conditioning reduces entropy.
But why does conditioning reduce entropy?
Because they are correlated.
So
Some sort of information
again we have okay, the claim is let's use the above definition. Which definition would you like to use?
h of x comma y is the h of x plus h of y given x.
Okay.
H of y comma x.
Okay, so let's see. You want to use h of x comma y, which is h of x plus h of y given x, which is equal to h of y plus h of x given y. Okay. Next.
And we say that intuitively we understand entropy as the number of bits used to encode x. So even if we have the bits for y, that would increase the number of bits.
Intuitively, that seems fine, but I want to prove. H of x is non-negative. Okay, so h of x given y is also non-negative. Okay. Okay, we'll revisit this a little later, but as of now, at least maybe some of you have already seen the fact that conditioning reduces entropy, but you still need to prove, right? That's why it's important to prove things. Also, the other important point is that many of these properties that we derive for discrete entropy, as we'll see later, don't hold true when we go into continuous random variables. So it's not enough to just rely on intuition alone. All right? Okay. The other important point is that h of x is invariant to the labeling of the alphabet. So in other words, if I have, let's say, 3 symbols, all right, if I have a probability mass function, p of 0 equal to half, p of 1 equal to 1/4, p of 2 equal to 1/4, and I have another distribution, let's say q, q of 0 equal to 1/4, q of 1 equal to half, and q of 2 equal to 1/4. Both these distributions have the same entropy. So it doesn't matter which symbols correspond to which probability. If you have the same collection of probability values, the entropy remains the same. All right? So the entropy does not depend on the alphabet, it doesn't depend on how the symbols are labeled. And that's, if you remember the experiment that we did in the very first class, right, when I took a source, a binary source, and compressed it using zip, even if I changed the symbols from 0, 1 to A, B or C, D, I would end up with the same, effectively the same compression length. Right? And as we've seen, the optimal compression rate is equal to the entropy. So how you label the symbols shouldn't really affect what is the final rate of compression, as long as you're doing things optimally. All right?
Sir, but shouldn't the rate depend, the entropy depend on the probability of each of the symbols?
It depends on the probability of each of the symbols. Correct.
For both of these to have the same entropy.
Correct.
Probability of getting 0 in the first distribution should be the same as probability of getting 1.
That's the point that I'm trying to make. It doesn't matter which symbol occurs with what probability. As long as the collection of probability, the probability multiset is the same for 2 sources, again remember, we're looking at the average compression length, right? We're not looking at the compressed length for symbol 0 or symbol 1 or symbol 2. So the optimal compression for both of these sources is going to give us the same expected length. Okay. Any other questions? Okay. The other property is that the entropy is a concave function of the distribution. How would you prove this? Okay, u log u is a convex function.
Minus u log u is a concave.
Correct.
Or rather, summation of u log u is also a convex function.
Correct.
So, derivative of that is a concave.
Correct. So the entropy is simply summation whatever x in script x of minus p of x log p of x, right? The function f of p, which is p log p, is convex. All right. I think we saw this in one of the early classes. Right. Even otherwise, you can just prove this by taking the second derivative and show that it is non-negative. Right. For all p greater than 0. The entropy is effectively negative of a sum of terms that look like p log p, right? And we've also seen that the sum of convex functions is also convex. So summation over all x p of x log p of x is convex. It's a convex function of p, the distribution p of x. Right? Remember that this h is a function of a vector, the probability vector. Right? So the entropy is effectively a mapping from px of 1 to px of m, where m is the size of the alphabet. Right, so p of x log p of x is convex, therefore the negative of this is concave. So the entropy is a concave function. Any questions? Fine. Since it's a concave function, it's going to be maximized at some particular point. Right? If there is a maximum, there's a unique maximum. How do you find the maximum of the entropy function?
Take the derivative and equate it to 0.
Sure, that's one way, but one thing you have to remember is that you also have to handle the constraint that the input or the argument should be a valid probability mass function, right? So when you try to maximize the function h, what you're actually trying to find is a constrained maximum. All right. So what is maximum of h of x. This maximum has to be taken over all, let's say p1 to pm, such that each pi is greater than or equal to 0, and summation over all I, pi should be equal to 1. Alright. Okay. So you may wonder why I'm doing this, why it's necessary to be careful in this case. Let's simply try to blindly find the derivative and set it equal to 0, and let's see what would happen. All right. What is in this case, when you say the derivative, it's actually a vector. It's a function of a vector. So you should take the gradient and set it equal to 0. All right. So what is that equal to? What is the partial derivative of the entropy with respect to the ith probability? It's equal to 1 plus log pi, or negative of this, something more. Remember the base is 2, right? So it's going to be pi divided by log 2, right? So this is the partial derivative. What happens if we just set this to be equal to 0? Yep. So what should pi be equal to? 1 by e. Does that give you a valid PMF? It doesn't, right? So that's why this is the incorrect approach. Because you're not taking care of the constraints that all of the probability should be greater than or equal to 0 and they should sum to 1. Right? So the correct way would be to try to maximize this using Lagrange multipliers by setting it up as a constrained optimization problem. Right? So that's one approach, and if you try to do that, you'll see that this is going to be achieved at, so the maximum of the entropy will in fact be equal to the log of the cardinality of x, and this is exactly equal to the entropy of the uniform distribution. So the entropy is maximized when the distribution is uniform. So as I said, one way to prove this is using Lagrange multipliers, but in just a few minutes I'll give a different proof which does not use Lagrange multipliers. So this is what will be called an information theoretic approach to proving such a result. Right? So information theory is of course it's used to say something about problems like data compression and communication, but it's also used to prove certain results about certain functions. All right? And we'll see an information theoretic proof of the fact that the entropy is maximized by the uniform distribution. And in fact, we'll see something a little more stronger than just that. We'll see that the entropy keeps increasing as the distribution gets closer and closer to the uniform distribution. So the more uniform like the distribution is, the larger the entropy is going to be. And the farther away you go from the uniform distribution, the smaller the entropy will be. Okay. So in fact, let's maybe try to run a simple experiment. Right. Let's try to construct some distributions and see what the entropy looks like. All right. In particular, let's take the class of distributions for which the probabilities decay as, say, some constant to the power of I. Right. So in other words, let's take the alphabet to be the set of integers from 1 to n. All right, and say n is equal to 20. Okay, and let's draw a probability mass function that looks like say 2 to the power of, or let's say for now even simpler, 1 divided by n plus 1. Okay, so it's 1 by I whole to the power, for now let's just keep this to be 1. Now this is not a valid PMF, so I have to normalize the probabilities. So let me normalize this and let me just plot. Maybe since it's a discrete distribution, I'll use plt.stem to see what the probabilities look like. It's something it's decaying as 1 over n. All right. So what happens as I increase this exponent? Let me call this k and set k to be equal to 2. We see that the decay becomes much faster, which is what you would expect. There's nothing surprising. And what happens when I take k to be equal to 0? I end up with a uniform distribution because all of the probabilities are exactly the same. Okay, nothing fancy over here. But now, for the same, let me try to compute the entropy for different values of k. Okay, I'm going to keep the alphabet size the same, but I'll keep increasing k from 0 to 2. k can also take non-integer values. That's not a problem, right? So as if k is very small, then it's very close to uniform. As k increases, it becomes farther and farther away from uniform. Whatever farther means, at least visually you can see that it's very different from the uniform distribution, as it is very sharp and peaked, right? So I'll vary this from 0 to 2 in steps of say 0.1. And let me store all of the probability, all of the entropies. In an array. This is minus sum of p times log of p. All right. Hopefully the code is clear. Oops. Sorry, there should have been a colon at the end. Great. So we see that as k increases, the entropy decreases. All right. So the closer it is to the uniform, the larger the entropy is. Right. We'll try to formally prove this. Question? Yeah. K negative. You can. That's again in you'll see that go in the opposite direction. Perfectly valid. So let's take say minus 2 to 2 to 0.1. So then instead of it being a sequence of decreasing probabilities, it will be a sequence of increasing probabilities. Right, and I need to change this. Minus 2. Right. So again, it decreases. Of course, it's not symmetric because the probability distribution is not symmetric. Right. But in any case, it's maximized when k is equal to 0. Right, and it's decreasing on either side. Okay, so to do all of this, we need some notion of distance between two distributions, right? And for that, I'll introduce a new term, which is there are of course different ways of measuring distances between two distributions. One is to take, say, the L2 norm of the difference between, because in the end, what is a probability distribution? or a probability mass function, you can represent that as a vector. So any distance between two vectors can also be used to measure distances between two probability mass functions. Right? So we can take the L2 norm, or in general any LP norm. That's one valid way of doing it. But what we look at is not really an actual distance in itself, but what is called a divergence. So this quantity, called the Kullback-Leibler divergence or the KL divergence, will reappear multiple times, and we'll see that each of these terms has an operational meaning. It's not just a quantity we define out of nowhere. I'll define the KL divergence first. So given any two distributions Px and Qx, on some alphabet finite, or more generally discrete. But these are not any PMFs. I'll require a technical condition such that Px of x is equal to 0 for all x such that Q of x is equal to 0. All right. If there's some symbol for which Q of x is equal to 0, then for that symbol P of x must be equal to 0. Just for mathematical definition. All right. Then the KL divergence, which I'll denote d Px, these two vertical lines Qx. So the KL divergence between P and Q is equal to sum over all x, Px of x log Px of x by Q of x. Right, so this is the KL divergence between P and Q. One thing you can observe is that this is not a symmetric function of P and Q. Right? So dQp is in general going to be different from dPq. So it's not symmetric and therefore not a true distance. If you take, say, the L2 norm or any LP norm, it's a symmetric function of both of the arguments. This is not. What happens when P of x is equal to Q of x? It's equal to 0, right? P of x by Q of x will be equal to 1. So log of 1 is equal to 0. Okay, great. Yeah. I mean, for all, when I say P equal to Q, I mean that P of x equal to Q of x for all x. Great. So to motivate this particular quantity, let's go back to the original, the optimal compression scheme that we studied, all right, but with a little twist. So let's suppose that again I have this source x or source xn, which I wanted to encode so I have the variable length compression problem, but now I don't know the true distribution P. So xn is drawn according to Pxn. I don't know what Pxn is. But I'll still go ahead and use a different distribution, Qxn. All right, so I design a compression scheme. I use the same approach of sorting the sequences in decreasing order of probabilities, but I don't know what the true probabilities are, so I'll sort them in decreasing order of Q probabilities. All right, so I'll sort them as xn of 1, xn of 2, and so on, such that Qxn of xn of 1 is greater than or equal to Qxn of xn of 2, and so on. Okay. The actual probability of xn of 1 may not be the highest. So according to Pxn, the probability of xn of 1 may or may not be greater than or equal to that of xn of 2. Okay. So Qxn is some distribution that the encoder and the decoder both know and they're going to use, but xn itself is drawn according to P. All right, great. And I'll do the same thing. So xn of 1 is going to be mapped to the empty sequence, xn of 2 will be mapped to 0, xn of 3 is going to be mapped to 1, and so on. Hopefully this scheme is clear. Right? I'm assigning the code words based on the distribution Qxn instead of Pxn. Okay, great. Now let's try to walk through the steps of the proof. In general, what will be L of the encoding of xn of I? This is again floor of log of I. Nothing has changed so far, right? But now I've assigned probabilities according to Qxn, right? So Qxn of the ith sequence is going to be less than or equal to 1 over I, because they're sorted according to Qxn, right? Or in other words, I is less than or equal to Qxn of xn of I. So if I take the expected length, right, what is this equal to? Oops. Yeah, summation over all xn of yes. Are you sure?
The expectation is taken over distribution P.
Correct. So the expectation has to be taken over the true distribution, right? Because we're trying to calculate the actual expected length. So this is expectation taken over the true distribution. So the probability that you observe the ith sequence according to distribution Pxn times the length of the encoding of the ith sequence. Which is sum over all I Pxn of xn of I. But now the length is equal to floor of log of I, and log of I is upper bounded by log of 1 over qxn of xn of I. Right? So this is less than or equal to log 1 over which is nothing but summation over all possible xn p of xn log 1 over q of xn. Right? Again, keep in mind this is only an upper bound, but still it's a good representative of what the expected length is going to be. It's going to be very close to this. Now, what I can now do is add and subtract the entropy. Right? Let me add and subtract h of px, the entropy corresponding to p, plus sum over all xn of pxn log 1 over qxn. This is nothing but the entropy plus sum over all xn. What is negative of entropy corresponding to Pxn? So it's P of x log P of x. So I have P of x log P of x plus P of x log 1 over Q of x, which is nothing but P of x log P of x divided by Q of x. Right, which is nothing but the entropy of the source plus the KL divergence between P and Q. Right? So what this is saying is that suppose that the true distribution is P, but for whatever reason you used a different distribution Q, then the expected length, the minimum possible expected length that you can achieve is of course it's equal to the entropy plus an additional amount, and this additional amount happens to be the KL divergence between P and Q. Yeah.
How does the ordering come into play here? So,
Which
like we said, Q is chosen such a way that the probabilities are.
no, the symbols are ordered in the decreasing order of their Q probabilities. Right? So in the end, what does the scheme look like? I have this table of sequences, right? In some order, doesn't matter what order it is. The first symbol gets mapped to the empty string, the second symbol gets mapped to bit 0, and so on. Right? In fact, any compression scheme can be represented in this particular fashion. You agree? Now the question is, so how do you order these symbols? Since I didn't know Pxn, I ordered them in decreasing order of their Q probabilities. Is that okay? Still, you have a question? Okay. So that is where Q comes into the picture, because I chose my table or ordering based on the distribution Q. Okay. So this distribution mismatch between P and Q, or misspecifying the distribution, led to this additional penalty in the expected length, and that additional penalty is precisely dpq. And you can't really do any better than this, because you don't know what the true distribution is. So you go by whatever you think the true distribution is. All right? Alright. So this is where the KL divergence comes into the picture. Okay. Or one of the places where the KL divergence comes into the picture. We will see that it again will arise in a totally different problem as well. Great. So that gives us some motivation to look at the KL divergence. But let's look at the definition again. So I have d px qx, which is equal to, as we just saw, this is equal to the entropy of px, or the negative of the entropy of px, plus summation overall x p of x log 1 by q of x. All right. Let's look at this when q of x is a uniform distribution over the same alphabet. So let's choose qx to be uniform over the alphabet script x. So d px, let's say ux, where ux is the uniform distribution, this is equal to minus h of px plus, what do you get? So q of x is 1 by the size, 1 by the cardinality of x. Right, so this is equal to summation overall x p of x log 1 by cardinality of x, or this is nothing but log cardinality of x. I can take log cardinality of x outside the summation, and I simply get minus h of px plus log cardinality of x. All right. What is the entropy of the uniform distribution? It's also log cardinality of x, right? So this is nothing but minus entropy of px plus entropy of ux, the entropy of the uniform distribution. So the KL divergence between px and the uniform distribution is equal to the entropy of the uniform distribution minus the entropy of px. Again, this happens only when the second distribution is uniform. It does not hold true in general. All right? In general, d of pq is not going to be equal to h of q minus h of p. All right? This happened only because this particular quantity, log cardinality of x, was a constant. I could take this outside, and I can replace this with any distribution, I still get the same quantity. All right? Okay, great. So I said that this dpq can be interpreted as the excess rate when there is a distribution mismatch, right? For this to make sense, dpq should be a non-negative quantity, because what does excess rate mean when dpq is negative, right? And we'll show that for any two distributions p and q, dpq is always going to be greater than or equal to 0. Alright. And one way of doing this is sort of rewriting dpq in a nicer looking form. So dpq is sum over all x p of x log p of x by q of x, right? I'll write this as summation over all x q of x times p of x by q of x log p of x by q of x. Okay? So this is equal to expectation with respect to the distribution q of p of x by q of x log p of x by q of x, where the random variable x is now distributed according to q. So you can think of this as expectation with respect to the distribution q of y log y, where y is equal to p of x by, again, I'm being a bit loose over here, you have to think about this a bit carefully. It's equal to p of x by q of x with probability q of x. When I say I'm being a bit loose here, you have to be a bit careful, because for the same, there could be multiple x that map to the same p of x by q of x. So you have to think about what happens in that case. In that case, you sort of combine the two together and you get the sum of the two probabilities. All right. So this is nothing but expectation of y log y, right? And what do we know about the function y log y? It's a convex function, right? Right. So y log y is convex, right? We just saw that a little previously when we tried to prove that the entropy is a concave function. So y log y is convex, which means that I can use Jensen's inequality. So, and the above is expectation of some function of y. This is expectation of some function of y, where f is y log y. So using Jensen's inequality, this is less than or equal to f of expectation of y. Because y log y is convex. But what is f of expectation of y? It's expectation with respect to the distribution q of p of x by q of x log expectation with respect to q, p of x by q of x. Let's try to evaluate expectation of y. This is equal to summation over all x p of x times, so I'm sorry, you're taking the expectation with respect to q. So the probability of occurrence of x is q of x times p of x by q of x. This q of x and this q of x gets cancelled. So this is simply equal to 1. Alright. So this means that this is 1 log 1, which is 0. Right? I'm sorry, I made a little bit of a mistake. So it's a convex function. So expectation of f of y is going to be greater than or equal to f of expectation of y. So dpq is greater than or equal to 0. All right. Maybe let's quickly go over it once again. So I have the KL divergence, which is p of x log p of x by q of x, summation over all x. I first express this as an expectation with respect to the distribution q of p by q log p by q. Right? Which is of the form expectation with respect to q of y log y. Since y log y is a convex function, expectation of y log y is greater than or equal to expectation y log expectation y. And expectation of y is equal to 1. So dpq is greater than or equal to 0. Alright. So it's a neat little trick. Right? But it allows us to prove that the KL divergence is always non-negative. Any questions? Yeah.
Is scalar divergence only defined for discrete or continuous also?
No, we'll define it for continuous random variables as well. So
But entropy is only defined for.
we'll see that. I want to treat these things separately. So we'll first talk about various information measures for discrete random variables, and then go into continuous random variables and see which of them have a reasonable interpretation and which don't, and so on. All right. But for now, let's try to internalize, let's try to even intuitively grasp what each of these terms mean. You can use a very analogous definition, because if you looked at both quantities, the entropy as well as the KL divergence, we defined them as expectations of some functions, which in principle you can also do for continuous random variables by replacing the PMF with the PDF. All right, that's perfectly valid, but many of the interpretations don't necessarily hold when you go to continuous random variables. So it's important to distinguish between which properties and which interpretations hold and which don't. And that's why we look at it separately.
But as a mathematical abstract, they are defined and we can use them.
They are defined, but some of the properties don't continue to hold. Right? For example, just to give you a very quick example, the KL divergence, non-negativity of the KL divergence will still continue to hold for continuous distributions, but the whatever quote unquote entropy for continuous distributions will not be non-negative. It's not guaranteed to be non-negative. It could be negative. All right. That's why it's important to treat them separately and look at them again. And in fact, we'll see how many of them are used for studying similar problems for continuous sources. Any other questions? Okay, great. So now this itself immediately gives us some nice consequences. The KL divergence is greater than or equal to 0, and we saw that for any distribution, the KL divergence between the distribution and the uniform distribution, this is equal to log cardinality of x minus the entropy of Px. Since the KL divergence is non-negative, this means that the entropy is always less than or equal to log cardinality of x. All right. So this is a one-line proof of the fact that entropy is maximized when the distribution is uniform.
So, for the proof of KL divergence being none,
Correct.
we could equivalently have negated the expression for the KL divergence and instead taken an expectation of the
True, I agree.
but I'm getting calculated
Then the direction of the inequality would change, right? Oh, so for what function are you going to take the...
log
Okay, so if you take expectation with respect to p,
of QA.
okay, so
Log QA.
so basically what you want to do is in this particular proof, right, instead of saying, you can write this as negative of expectation of log q of x by p of x. Expectation taken with respect to p, right? So this is equal to negative expectation with respect to p of log q of x by p of x, right? Log is a concave function, right? It's not a convex function. Now again, you can use Jensen's inequality, but you also have an additional negative sign. So this is going to be greater than or equal to log of expectation with respect to p of q of x by p of x, which is equal to log 1, which is 0. Right? So that's a perfectly valid other way of doing this. Any other questions? That's a good point. That's another way of proving that the KL divergence is non-negative. Okay. So, I mean, this was sort of a straightforward application of the fact that KL divergence is non-negative. There are more interesting ways of using the same property, and so let's see one of those. So this is an upper bound for distributions over a finite alphabet, right? What happens when the alphabet is not finite? Now, if the alphabet is not finite, the notion of uniform distribution doesn't make sense anymore. Right? So let's see what happens. So let's take any x which is distributed over, say, the natural numbers. Okay, so it takes values 1, 2, 3, all the way up to infinity. And with PMF Px, so Px is some probability mass function, and we'll assume that the mean of this random variable is bounded. It's equal to some quantity, which is finite. expectation of x is equal to mu. What can you say about the mean? What range does mu lie between? In particular, can mu be less than 1? I need a more confident answer. No. Why? Yeah, the range of x is from 1 up to infinity. So x is greater than or equal to 1 with probability 1. So the mean should also be greater than or equal to 1. So this quantity is something that is greater than or equal to 1. So I've chosen the natural numbers. All right. Great. So among all possible PMFs on the natural numbers with mean equal to mu, which distribution maximizes the entropy? All right, that's the question we want to answer. All right. Whoever said it's Poisson, it's not Poisson. So the claim is that it's maximized by the geometric distribution. All right. So let's take qx of I to be equal to some alpha times 1 minus alpha raised to I minus 1 for what is the mean of this particular distribution and what is the entropy of this distribution? I'll leave that as an exercise. Claim is that this mean is equal to 1 over alpha. All right. This is for the, how do you interpret the geometric distribution?
First success in the trial.
Correct. So you toss a coin with probability of head being equal to alpha. So qx of I is the probability that you have to toss the coin I times in order to get the first head at the ith toss. Right? Okay. So for this, I want you to compute the entropy of qx, but let's also compute the KL divergence between px and qx. All right. This is equal to, again, the entropy of px plus sum overall x equal to 1 to, or let me label these, I equal to 1 to infinity px of I log 1 by qx of I. Right, so this is minus the entropy with respect to p of px plus sum over I, px of I log 1 over alpha times 1 minus alpha raised to I minus 1. sum over I of, I'll split the log term into two, px of I times log 1 over alpha plus log 1 over 1 minus alpha times I minus 1. Right? Which is minus entropy of Px plus summation over I of, okay, let's Px of I log 1 over alpha plus sum over I Px of I times I minus 1 log 1 by 1 minus alpha. What is the first term? Or the second term over here? It's log 1 by alpha, right? Plus, what happens to the rest? It's log 1 by 1 minus alpha times, I have summation over I of I Px of I, which is expectation of x with respect to Px, which is nothing but mu minus 1. And how did we choose alpha? What is alpha equal to? It lies between 0 and 1. But I wanted to choose Qx such that it has the same mean as Px, because I'm comparing two different distributions with the same mean. Right? And the mean is equal to, the mean of Qx is 1 by alpha. So I want this to be equal to mu. So I should choose alpha equal to 1 by mu. Right? So this is equal to minus entropy of Px plus log mu plus log, you can see this is mu by mu minus 1 times mu minus 1. Let me try to write it in a different way. I'll leave it as it is. I'll replace mu by 1 by alpha. This is equal to minus h of Px plus log 1 by alpha plus alpha minus 1 by alpha log 1 by 1 minus alpha. I'm sorry, 1 minus alpha by alpha. And this is equal to alpha by alpha. Right? So this is minus entropy of Px plus 1 by alpha times the binary entropy of a Bernoulli random variable with parameter alpha. Or mu So this quantity alpha log 1 by alpha plus 1 minus alpha log 1 by 1 minus alpha, this is just the binary. Okay, I leave it as an exercise to show that this is equal to the entropy of Qx. We know that this quantity is greater than or equal to 0 because it's the KL divergence, which means that the entropy of any distribution on the natural numbers is less than or equal to the mean times the binary entropy of 1 over the mean. All right. Okay. Let's stop here. We'll continue in the next class.